All right, so we're going to look at a bit more of this geometrical representation of a complex number. So rather than an algebraic representation. Now, we've already talked a little bit about this, how that yes, we can plot on the Argand diagram a particular point, but we can also think of it as a vector. And so here's a complex number. Its Cartesian coordinates would be xy. We could draw in the vector, we could work out its length, and we could work out its argument that it makes, and that would be it in the mod arg form. And what I said at the time when we first looked at this idea, if you remember, the advantage of thinking of it as this line rather than the point, if I move the point somewhere else, it becomes a different number because there's only one point. But if I slide the line around, so just through translations, it's always going to have the same length and make the same angle. So it doesn't matter where I put that line. Right? So I could put it there. It still has the same length. It still is at the same slope. So it still represents the same complex number. I can put it there. Again, still got the same length. Still has the same slope. So it still represents the complex number. But the question becomes, which complex number is it? How do you work it out? And the way you always work out a complex number with a vector is what we call head minus tail. So whatever the number is at the head of the vector, x plus iy, minus the tail. So when it's joined to the origin, it is the same as the point because you're saying subtract 0. But as soon as you slide it somewhere else, you go head minus tail, and it will come up with the same answer because the slope is the same. So the rise over the run is the same. So we must get the same. So no matter where it is, that length and the argument will remain constant. So how do we add and subtract using this idea of vectors? So there's one complex number, z1. Another complex number, z2. If I want to add them, it's a matter of just sliding or translating one of the vectors, and we place them head to tail. So we put the tail of one on the head of the other. So I can move the blue one over there. That position, that green one, would become z1 plus z2. If I join up to the origin, the green vector is also z1 plus z2. And we know it doesn't matter what order you add in. I moved the blue one to the red one, but I could have just as easily moved the red one to the blue one, and I still end up at the same point. In fact, get a parallelogram there. To subtract, you place them head to head. So it's like adding the negative vector. So down here, this black point here, would be z1 minus the z2. So instead of placing the tail on z1, I place the head on z1, and where it ends up is down here. Join that to the origin, and that would be the vector z1 minus z2. And there's another position that would very easily fit in. And that's the other diagonal of that same parabola. Has to be, because remember we said any vector is head minus tail. So I could say z1 minus z2. I could also say z2 minus z1. It depends in which direction we're going, as to which end's the head, which end's the tail, as to which one it would be. All right, there's this thing called the triangular inequality, a very simple idea. You've got a triangle. Any particular side will be shorter than the sum of the other two sides. And the basic idea, of course, is the shortest distance between any 2 points is a straight line. So if you were to go off at an angle and come back and form a triangle, that's obviously got to be a longer distance than just going straight between the 2 points. So triangle ABC would have been nice if I labelled them. Then AC will always be less than or equal to AB plus BC. The equality will happen when AC is a straight line. So if all those were in a straight line, then the distance from A to C would be the same as the distance from A to B and then B to C. Why do I bring that up? Because we can use that idea to prove this. The modulus of Z1 plus Z2 will always be less than or equal to the modulus of Z1 plus the modulus of Z2. Remember, the modulus is the length of the vector. There's a triangle there where one side has its length Z1 plus Z2. That's the green vector. One has length Z1. That's the red vector. And one has the length Z2. That's the blue vector. So there's a triangle here. So any side, I've picked the green side, must be shorter than the sum of the other two sides. And so that's how we can very easily prove this. And if we use that idea, we can simply say, well, by the triangular inequality, this must be true. So let's look a little bit more about addition. So point A represents Z1, point B represents Z2. So as we just saw, C will end up representing Z1 plus Z2. OACB ends up being a parallelogram because they've got to be the same slopes, therefore they're parallel. Subtraction, as I said, if point D represents the negative of Z1, so we get our vector but go in the opposite direction. So negative Z1 is over here. And then point E represents Z2 minus Z1. So let's have a look at that closely. We can think of it as two ways. Here's vector Z2, and I have subtracted vector Z1. So going back the other way around. Or no, wrong way. Now, the length of AB then becomes the modulus of Z2 minus Z1, because it's the length of the vector where we've gone Z2 minus Z1. The argument of Z2 minus Z1 I've called alpha. Let's put it in a bit more practical sense. Let's have a look at an actual question that was asked a long time ago now. But the sort of things that we could be asked by manipulating vectors and what have you. So here's our Argand diagram, the complex plane. PQ represents Z and W respectively. So in fact, they're reminding us that, hey, the length of PQ then would be the modulus of Z minus W. Because if I was to join PQ, that vector, head minus tail, I could think of as Z minus W. Also, it could be W minus Z, but it doesn't matter because we're talking absolute value. So Z minus W, W minus Z, same thing. So it really doesn't matter which direction I'm going here. Show that the modulus of Z minus W will always be less than or equal to the modulus of Z plus the modulus of W. That's what I was just talking about with the triangular inequality. So let's draw in that other vector, PQ there. So how would I explain it? I'd say something like this. Well, I know the length of OP will be the modulus of Z, because that's the length of that vector. And OQ would be the modulus of W, the length of that vector. And our third vector would have the modulus of Z minus W. Well, they even told us that. And so then I can simply say, well, okay, we're using the triangular inequality on that triangle. Any particular side, I've chosen the side that has length modulus of Z minus W, must be less than or equal to the sum of the other two sides, mod Z plus mod W. Now they want us to place the point R, and it will represent Z plus W. So we've got to put it somewhere, and then they ask, well, what can be said about our quadrilateral? So if I want to get Z plus W, then, there we go, I create my parallelogram, which also then gives away the answer. So the next bit, but we add either, you can think of it as either adding the vector OQ onto P, or adding the vector OP onto Q, but we end up at the same point. And so that one, OR, would be the vector Z plus W. What can be said about the quadrilateral? Well, it's a parallelogram. We know that. We know it's a parallelogram. If the modulus of Z minus W is equal to the modulus of Z plus W, what can be said about W divided by Z? Okay. So they're telling us these two things are equal. The length of Z minus W is the same as the length of Z plus W. Those two vectors in regards to our parallelogram are what? The diagonals. So they're telling us in our parallelogram, the diagonals are equal. What is a parallelogram where the diagonals are equal? Yeah, rectangle. So diagonals are equal. We know the shape is a rectangle. Therefore, that angle must be 90 degrees. Because if it is a rectangle, and have a look at the picture, I haven't got it here, but if you look at the argument of W minus the argument of Z, so look at the origin. Argument of W minus the argument of Z, that is the angle in the rectangle. So it must be 90 degrees. But we said argument W minus argument Z, I can write it as one argument. It's the argument of W divided by Z. So I now know the argument of W over Z is pi on 2, or 90 degrees. What can be said about W on Z? Yeah, got to be imaginary. Its argument is 90 degrees, or pi on 2. So we can say W on Z is purely imaginary. Let's have a little bit of a look at multiplication. We saw this before, this idea that, hey, it doesn't matter which order we do it in, we can find the modulus first, then multiply, or vice versa. And we saw that when it came to the arguments, we actually added the arguments when we were multiplying. So as far as our picture goes, let's put it in mod arg form there. R cis theta 1 times R2 cis theta 2, we end up with R1 R2 cis theta 1 plus theta 2. So if we multiply Z1 by Z2, if we think of our vector, vector Z1 will be rotated anti-clockwise by whatever the argument is of the other one, so by theta 2. Whatever its argument is, will rotate that vector. Its length will be stretched or shrunk depending on what we're multiplying by. It'll basically be multiplied by the modulus of the other vector. So if the other vector had a length of 1, well then it would stay the same. If it had a length of something bigger than 1, the vector would get longer. If it had a length smaller than 1, well, we'd be multiplying by a fraction, it'll get shorter. So there's a bit of a visual look at that. So if we multiply Z1 by cis theta, notice it's just cis theta, the modulus is 1 in this one. So the length of the vector won't change, because when we multiply the moduli, well, we're multiplying by 1. The vector OA will rotate anti-clockwise an angle of whatever theta is. And so our new one, the point B there, would be Z1 times the cis of theta. So we just rotated whatever theta is. Oh, sorry, I also put there, if it was by R cis theta, that's when the length of the vector is going to change. Okay. Now here's a really important idea then, and we've talked about this. If that rotation is 90 degrees, we end up multiplying by I, because cis 90, or cis pi on 2, turns out to be I. You got cos plus I sine. Cos of 90 is 0, sine of 90, so we're just multiplying by I. So IZ1 will rotate at 90 degrees. So multiplication by I, rotation by 90, and keep in mind any power of I, whatever the power is, that's the multiple of 90 that you're rotating by. So negative 1, 180, because that would be I squared. However, vector is head minus tail, so I'll mention that again. That's important. So here I've got a shape. We know D is the point 1, A we're calling omega. And I think it's meant to be a square. I didn't write it there, but I think from memory this shape is a square. Yes, it must be, because I'm saying vector. Now here's how we write vectors. Vector DC. Arrow on the top, the arrow is in the direction of the vector. So D is the tail, C is the head. So we're saying DC. We're going from D to C. And DA, D again is the tail, A is the head. So what we're saying here is this vector DC is the vector DA rotated by I. The length has stayed the same, but we've rotated it 90 degrees. Another thing I notice here, I could also say, if I want to work out now what is the point C, well, hang on, DC, that vector, is head minus tail. So it would be whatever C is, minus 1. And DA will also be head minus tail. So it will be omega minus 1 times I. So making C the subject, that's the best I can do. I don't know what omega is, but it'll be 1 minus I plus I times whatever omega is. That would be the value of C. Now, if I wanted to work out B, I could say, well, hang on. B, to the point A, I've added this vector, which is the same as the vector down here. So same as the vector DC. So it's like I've added DC onto A. So to the point A, I've added the vector DC. Well, A we said was omega. DC was C minus 1. But we also have just worked out what C was. So tidying that up, we end up with a final answer there of minus I plus 1 plus I omega as an answer. Whoop. Another way I could have worked out B. I could have said to the point C, I've added on the vector dA. Should get me the same answer. So C, we worked out to be 1 minus I plus I omega. We're adding the vector dA, so head minus tail, omega minus 1. Tidying that all up, we again come up with the same answer for B. There's another way I could work out B. I could say the vector dB. So imagine I've drawn in that diagonal. The vector dB would be the vector dA, and I would have rotated it. Remember, this shape is a square. So I know the diagonal will cut the vertex at 45 degrees, or pi and 4. So I know I've rotated at 45 degrees, so there's my cis pi and 4. But the length will change. And if you go back to your basic 45-degree triangle, we know the sides are in the ratio 1, 1, root 2. So the diagonal will always be root 2 times the length of the side. And so I'm saying, well, okay, so I know the length of my vector will be multiplied by root 2. Let's see what happens. Root 2 cis pi on 4 times dA, which is omega minus 1. Well, cos pi on 4 is 1 on root 2, so is sine pi on 4. The root 2's then cancel, leaving me with just 1 plus I. So I have 1 plus I times omega minus 1, plus the 1 that I'm now moving from the other side, because the vector dB, head minus tail, is B minus 1. And tidying that all up, eventually, once again, we come up with the same answer. Right? So it's just thinking about how we move the vectors to come up to this new position. And there are different ways of thinking about the same problem. Here's one from the 2000 paper. This one's a rectangle, they tell us. A is omega, and the length of OC is twice the length of OA. And, well, that's all they've told us. First part of the question is then, well, what would be C? What complex number is C? So how do I get C from the information I've got? Well, the only information I've got is that A is omega, and this is a rectangle. So to get to OC, to create the vector OC, I've got the vector OA. I've rotated it 90 degrees, so that's multiplication by I. But the length of the vector is doubled, because we said OC was twice OA. So I've multiplied it by 2I. So let's substitute in. Vector OC, well, these ones are a lot easier because we're joining them to the origin. So the actual point is the same as the vector. So OC will just be C, OA will be omega, so C must be 2I times omega. That would be the point C. What complex number corresponds to the point of intersection D of the diagonals OB and AC? Okay. We know diagonals in a rectangle will bisect each other. So this point that we're talking about, I could think of it either as the midpoint of AC or the midpoint of OB. Either way, it should come up with the same answer. So I'm going to say it's the midpoint of AC. Because to do OB, I'd have to know what B is. And at this stage, I don't know what B is. Okay. So how do we find the midpoint? We add them together, divide by 2. Remember, A, the point A, it is a set of coordinates. I don't know what they are. It's omega, but it would have a real part and an imaginary part. It would have an x-coordinate and a y-coordinate. And the same with the point C. So I'm just saying, okay, we get these two numbers. We're going to add them together, divide by 2. That will find me the midpoint. A is the point omega. C is the point 2i omega. And we're going to divide that by 2. So best I can do with this one until I know what omega is anyway, it would be, well, D will be a half plus I times omega. Okay, some more examples. We know in this question, OBA is an equilateral triangle. Side lengths 1, which makes the maths nice and easy, so the length of the vectors there are 1. OBCD is a square. We want to find the complex numbers represented by the points B, D, and C. Odd way of asking that question. Perhaps they're giving me a hint, as in the order find these, because why wouldn't they say B, C, D? They've said B, D, C. So if you see something like that, I think that's a bit strange. There must be a reason why they've written it that way rather than the other way. Maybe they are giving us a hint. We're going to find them in the form x plus iy. There must be a point there that we know then. And there is a couple of points that we know. What are they? We know A, someone said. What's A? Yeah, because we said the length of those are 1, and it's lying completely on the real axis. So the length is 1. A must be at the point 1. What's the other one we know? B. O, I was going to say. We know O is the origin, so that's going to be naught. We don't know B yet. We've got to work that one out. So. Okay. So let's work out B. I think the hint that we didn't know B was in the question, where it said, find the complex number represented by B. I think that was a bit of a hint. Okay, so we're going to find B. If I look at the vector OB, I've got the vector OA. I know the lengths are the same, because it's an equilateral triangle, they said. But I've rotated it 60 degrees, because the angle in an equilateral triangle will be 60. So I know I've got vector OA, and I've multiplied it by the cis of pi on 3. Okay, let's substitute everything in then. Again, it's joined to O, which makes it nice. So OB is the same as B. OA, well, that's just 1. And cis pi on 3. So B must be the point. Cis pi on 3. They want it in the form x plus iy. So the cosine of pi on 3 is a half. The sine of pi on 3 is root 3 on 2. So there's B. D. I could do it two ways now. I could say, well, you can see the one I've done it here, is vector OA is OB rotated 90 degrees because of the square. I could have also said it's OA rotated, what's that going to be? 150 degrees. So I could have done it that way as well. Okay, so D will simply be I times B, because rotation are 90 degrees. And that's why I picked that way, because it's just multiplication by I. Very easy. So I'm going to get minus root 3 on 2 plus a half I. Okay. Let's now find C. And again, we've got several ways we could find C. I could say I've got OB rotated 45 degrees, but lengthened by root 2. I could add, as this is the one I've done, I could add the vector OD to the point B, but I could also add the vector OB to the point D. That would also work. So C is equal to B. B we worked out was a half plus root 3 on 2I. The vector OD is D minus O. D we've just worked out is minus root 3 on 2 plus half I. Add them together, and we've got this lovely expression here. 1 minus root 3 on 2 plus 1 plus root 3 on 2I. Okay. But wait, there's more. The points A and B in complex plane, there's Z1 and Z2. Triangles OAP and OBQ are right-angled isosceles triangles. Explain why P corresponds to the complex number 1 plus I Z1. So P is up the top there. How did we get 1 plus I Z1? Oh. Well, I've said, let's have a look at the vector AP. The vector AP would be the vector AO rotated 90 degrees, but I'm going in a clockwise direction rather than an anti-clockwise direction. So I've multiplied it by minus I instead of plus I. Sub in, head minus tail. So AP would be P minus A, minus I times 0 minus A. So P minus Z1, because A is the point Z1, minus I times minus Z1. Rearranging that, there it is. P is Z plus I Z1, or to answer the question, 1 plus I times Z1. We're looking for, oh, notice there is no part 2, it's actually part 3. Part 2 is too easy, okay? Let M be the midpoint of PQ. What complex number corresponds to M? Well, if M is the midpoint of PQ, I've got to find Q. That probably is what part 2 was. So, similar idea, vector QB will be vector BO, rotated 90 degrees, but this time it is in the anti-clockwise direction. So Q minus B, I times O minus B, very similar to the last one, but this time we get 1 minus I times Z2. M is the midpoint of these 2 points. Add them together, divide by 2. So it'd be P plus Q divided by 2, and there's our answer. I probably rearranged it into real and imaginary, did I? Yes, I did. So we get Z1 plus Z2 plus Z1 minus Z2I all over 2.
But,
But yeah.
what's the point of that? Because they're all complex anyway.